In this video, we're going to be looking at the complex numbers. In particular, we're going to be focusing on equations whose solutions can't be found if you restrict yourself to just the real numbers. So we're going to extend to the complex numbers. Here's a reminder of what we mean by complex number. A complex number is a number of the form a plus bi, where a and b are real numbers and I represents the principal square root of -1. So I've already railed on how I dislike the names real and imaginary. Add complex to that list. Don't interpret complex to mean complicated. It's just a name that was given to this type of number. A complex number is a number that is the sum of a real part and an imaginary part. All of the real numbers are complex numbers. All of the purely imaginary numbers are complex numbers. Complex here doesn't mean complicated. Don't read into the name. It's just a label. In a prerequisite course, you learned how to do arithmetic with complex numbers. You added them, subtracted them, multiplied, divide. You probably talked about high powers of I. We might use a little bit of that when we're checking solutions, but the only real rule we need is how to simplify the square root of a negative number. So I've got a formal rule written here. I'm going to let a represent a positive number, a is greater than 0, and talk about how we can simplify the square root of the negation of a, which would be a negative number. If a is positive, then its negation is negative. We can rewrite the square root of the negation of a as the square root of a times the square root of -1. And we said on the previous slide that we use I to represent the square root of -1, and so we can simplify this to the principal square root of a times I. This is really the only fact from a prerequisite course we'll need in order to solve the equations that we're talking about in this section. Again, that other arithmetic you learned we might use if we were checking our solutions, but for the purposes of this video, we just need this fact. Let's look at an example that can't be solved if we restrict ourselves to the real numbers. The equation x squared plus 25 equals 0 can't be solved using a positive number or a negative number or 0. Obviously 0 doesn't work. 0 squared plus 25 is 25. And if you plug a positive or a negative number in for x, when you square it, you're going to get a positive result, and a positive number plus 25 is not going to be 0. So we know the answer can't be negative, positive, or 0. What are we going to do? Well, if we allow for complex solutions, we can solve this equation. Factoring isn't going to work. If we could factor this using integers, then the solution would be either a positive or a negative number. So we're stuck there. Using integers, you can't factor this left side. We could use the quadratic formula, but there's a better way to do this in my opinion, and that's extraction of roots. I'm going to swing the 25 over to the left side by subtracting it, and rewrite this equation as x squared equals -25. Isolating the squared term, the standard strategy for extraction of roots. Now at this point we consider cases, but you might not be as comfortable here, so I'm going to take when we use extraction of roots in a case like this, we have to consider both cases. So we use plus or minus to indicate that, and we consider the square roots of -25. Now you might say -25 doesn't have any square roots. That's true if you restrict yourself to the real numbers, but if we broaden our scope to the complex numbers, we can use that previous rule to simplify this. We can rewrite the square root of -25 as the square root of 25 times I, and now we know the principal square root of 25 is 5, so we get two solutions, positive 5i and negative 5i. Now, none of the techniques that we use in this section are going to generate extraneous solutions, so I'm not going to check every single problem. But let's check this one just to remind you of the arithmetic here. Let's start by checking our solution, positive 5i. If I plug that back into the original equation, I get 5i squared plus 25, and that's supposed to be equal to 0. Well, how do you square 5i? Well, you would square the 5, and you would square the I. You get 25i squared. And here's where those powers of I come in handy. What does I squared equal to? Well, we know that I is equal to the principal square root of -1. So I squared would just be -1. You would just square both sides of that. So you get 25 times -1 plus 25. And of course that's -25 plus 25, which really is 0. The same thing happens with -5i, because when I square -5i, -5 squared is also 25, I get the exact same check. So both of these really are solutions. So that arithmetic that you learned comes in handy when you're checking your solutions, but we won't need it otherwise, which is why we didn't review it. Let's look at another example. This one says the square of the binomial x plus 7 equals negative 16. This one looks like it's set up to use extraction of roots. Again, we do have the option of multiplying this out, swinging the 16 over, and using the quadratic formula. But when the problem looks like this, I'm thinking extraction of roots. Again, I'll show my work since this is a little strange. I say that x plus 7 is equal to plus or minus the principal square root of negative 16, considering both cases. The principal square root of 16 can be simplified. This is the square root of 16 times I. And we know the principal square root of 16 is 4, so this is plus or minus 4i. And now don't make a fuss about how to finish this off. Remember that 4i and negative 4i are just numbers, so to get the x alone you do the same thing you would always do. You subtract 7. There's kind of a tradition to put the real part first and the imaginary part second, so the standard way to write our answers would be negative 7 plus or minus 4i. There are two solutions there, negative 7 plus 4i and negative 7 minus 4i. And if you check them, you'll see that they really do solve this equation. Let's look at an example where we can't use extraction of roots. This equation has a linear term, a term with just an x in it, and because of that, extraction of roots isn't going to be easy to pull off. Subtracting the x over and dividing by 2 won't do me any good because I'll have variables on both sides. So instead, we're going to use our other strategy of getting 0 on one side and see where we're at. So I add 7 to both sides, and I get 2x squared plus x plus 7 equals 0. Now after a moment's thought, you'll see this doesn't factor. I'm not even going to pretend like it does. So we're just going to jump straight into the quadratic formula. So the quadratic formula says that we take the negation of b, so b is implied 1 here, so negative 1, plus or minus the square root of b squared, so 1 squared, minus 4 times a times c. That's 4 times 2 times 7, all over 2 times 2, 2a. So simplifying that, that's negative 1 plus or minus the square root of 1 minus 4 times 2 times 7 is 56, all divided by 4. And now it becomes clear why we weren't able to factor it. In order to guess the factors, we would have had to recognize that the factors included the square root of negative 55, which wouldn't immediately come out to me without using the quadratic formula. And I guess this answer is okay, but it's usually expected that you get that negative out of the radical, and that's where that rule comes back in. I can rewrite this as the square root of 55 times I. Notice that the I is not underneath the radical. We didn't have to worry about this in the previous two examples because we were able to find the square root of the number underneath the radical. Here the radicand is not a perfect square, so we have to leave the radical in our answer. So make sure that I is not underneath it. In fact, some people write the I on the left just to make it clear that the I is not underneath the radical. I don't do that. A textbook will usually take this one more step and write it in the a plus bi form. So they divide the negative 1 by 4, they divide the square root of 55 by 4, and they tack the I onto the last term. These two answers are equivalent, but the last one's written in the more formal manner, the a plus bi form. So there's a set of 3 equations that required an extension to the complex numbers in order to be able to solve them. That's really why the complex numbers were discovered or invented, however you want to think about it. Some nerds back in the day were trying to solve equations and they were coming up with techniques, and these imaginary numbers were coming out in their techniques. They weren't calling them that at the time, but they recognized that these complex numbers helped them solve equations, and then later on some other nerds figured out that there are applications for this in the real world. They come up a lot in physics and electronics and stuff. Now doing those applications isn't part of our course, I can't do any of that. But there's one type of example I like to do that will make sense of something that bothers a lot of people. So let me set this up for you first and then we'll go to the problem. If you ask somebody to find the square roots of a positive number, they can usually identify that there are going to be 2 of them. Like if I asked you for the 2 square roots of 4, you would recognize that you have positive 2 and negative 2. But when you jump up to cube roots, you can usually only come up with 1. Like if I asked you to find the cube root of 8, the obvious one is 2. 2 cubed is 8. But if there are 2 square roots of a positive number, it would stand to reason that there should be 3 cube roots. There really are 3 cube roots of 8. There's the one obvious one that we come up with, which is 2, but there are 2 more. And it turns out that those other 2 aren't real numbers. They live in this extension, this set of complex numbers. How can we find those? Well, let me demonstrate one way to do this using algebra. If I want to find the cube roots of 8, then I want to solve the equation x cubed equals 8. If x is a cube root of 8, then x cubed equals 8. And your normal strategy here of extraction of roots won't work. But there are two more. How do we find them? This process didn't work. This only gave us the real root. How do we get those complex roots that aren't real numbers? Well, the trick here is to get 0 on one side and use the factoring formulas for the difference of cubes. I've put both the difference of cubes and the sum of cubes formula on the screen here in case you don't remember them, but we're going to use the first one in our example. The difference a cubed minus b cubed can be rewritten as a minus b times a squared plus ab plus b squared. Some people call this the SOAP formula because of the pattern of the signs. The sign is the same, that's the S. The sign is the opposite, that's the O. And the last sign is always plus or always positive. Some people call this the SOAP formula because of that. It doesn't help you remember the terms. We're going to use this. So let me set up the equation again. We know that if x is a cube root of 8, then x cubed is equal to 8. And now I'm going to subtract 8 from both sides. Get 0 on one side. That's our standard strategy, right? Extraction of roots didn't work because we can't guess the other cube roots. But if I write it like this and use the difference of cubes formula, I can get those other two solutions. So to get the binomial, I just have to come up with something I can cube to get the first term and something I can cube to get the second term. Well, I can cube x to get x cubed, and I know I can cube 2 in order to get 8. It's the one cube root that I know. Minus sign between them because the sign is the same. To get the terms of the trinomial, I just use the pieces of the binomial. So I start by squaring the first term of the binomial. So I square the x, that's x squared. Then I take the product of those two pieces, but change the sign to plus. So x times 2, that's 2x. And then the last term is the square of the second term of the binomial. So whether you think of this as 2 or negative 2, its square is 4, so that's plus 4. Now we can use the zero factor theorem. So either x minus 2 is equal to 0, or x squared plus 2x plus 4 is equal to 0. And the first equation is easy to solve. That's x equals 2, which is the cube root that we already knew. That's the one that we were able to get by using extraction of roots. To solve the second equation, we can't factor it using integers, so we're going to fall back on the quadratic formula again. X equals negative b, that's negative 2, plus or minus the square root of b squared, save space here, that's 4, 2 squared is 4, minus 4 times a is 1 times c is 4, all divided by 2a, that's 2 times 1. Again, let me save some space here and do this arithmetic mentally. 4 minus 4 times 1 times 4 is 4 minus 16, that's negative 12. So this is negative 2 plus or minus the square root of negative 12, all divided by 2. And I can rewrite that as negative 2 plus or minus the square root of 12 times I, all divided by 2. And that answer is okay, I guess, but we can actually take this a little bit further to look a little bit nicer. So the square root of 12 can be rewritten as the square root of 4 times the square root of 3. And the reason I would do that is that the square root of 4 is 2. And now I can cancel all of these 2's. So negative 2 divided by 2 is negative 1. And these 2's cancel as well. And we get negative 1 plus or minus the square root of 3 times I. So let's write this cleaner on another slide. What are the cube roots of 8? Well, there's the obvious real number, 2. But there's also negative 1 plus the square root of 3 times I. And there's negative 1 minus the square root of 3 times I. So as you might have guessed, 8 really does have 3 cube roots, and in fact every positive and negative number has 3 cube roots. There's a real number that works, and there are always these two non-real ones. And you can take that up the line. So a positive number has 2 square roots, it has 3 cube roots, it has 4 fourth roots. I didn't word the problem this way. I said find all solutions to the equation x to the fourth equals 1. But another way to ask this question is to say, what are the fourth roots of 1? We want to find all of the fourth roots of 1. We know that using extraction of roots won't work. Even if you remember the plus or minus, that's only going to give you 2 of the solutions. We expect there to be 4, because it's a 4th degree polynomial. So what do? We get 0 on one side. x to the fourth minus 1 equals 0. That's a difference of squares in disguise. X to the fourth is x squared squared. So we can factor this to x squared plus 1 times x squared minus 1. And I guess we could factor the second part further, but I'm just going to set each of these factors equal to 0 using the zero factor theorem. And then I'm going to swing those constant terms over. X squared equals negative 1, x squared equals 1. And now I use extraction of roots. Here I can use the plus or minus. So this is x equals plus or minus the square root of negative 1, which is plus or minus I. This is x equals plus or minus 1. So there are 4 solutions. There's negative 1 and 1, which you probably could have guessed. Negative 1 to the fourth is 1, positive 1 to the fourth is 1. But there's also I and the negation of I. I to the fourth is 1. The negation of I to the fourth is 1. This equation has 4 solutions, or again, another interpretation of that is that 1 has 4 fourth roots. So while we can't get into any of the real-world reasons why people use complex numbers, we can at least investigate a couple of math ideas using them. Okay, I think that's enough to conclude our discussion on complex numbers. If you have any questions about the equations we solved here or any practice problems that you're trying, let me know.